In this video, I'm going to talk about mole ratios and how we use that to figure out the amount of reactants or products that is needed for a particular chemical reaction. Just to start with a bit of review, remember that chemical equations are balanced to satisfy the law of conservation of mass because the atoms that go into the reaction, the reactants, are equal to the atoms that come out, or the products. The exact number of atoms stays the same, but the number of molecules may change because atoms will be rearranged in a chemical reaction. Chemical equations also show you the relative amounts of the reactants or products by the coefficients that are in front of the formulas in a chemical equation. And those coefficients, those big numbers, can be thought of as the molecules of each that's needed for the chemical reaction, or they could be thought of the mole of each reactant or product, because you now know that a mole is a package of atoms with the same number of atoms. That's 6.022 times 10 to the 23rd. That very big number represents a mole because a mole is a word meaning a certain number. And once you have moles, you know we could convert it to actual numbers of particles, because usually we're not working with exact moles. Or you can make calculations to how many grams are involved using the atomic mass numbers on your periodic table. And we will be doing this quite a bit as we move into stoichiometry calculations. So let's consider ammonia. Ammonia is produced from hydrogen and nitrogen gas, and it has this formula that says N2 plus 3H2 will give us 2NH3. So we can look at this formula. Remember, we have an invisible 1 in front of the nitrogen here, the nitrogen gas, N2. So we can say that there is 1 molecule of nitrogen gas, N2, reacts with 3 molecules of hydrogen gas, H2, to make 2 molecules of NH3, or ammonia. But because those coefficients can represent more than just individual molecules, we can also think of them as meaning 1 mole of NH2 particles reacts with 3 moles of H2 particles to make 2 moles of NH3. And then because we can convert from moles to grams by using the atomic masses on the periodic table, we could even go so far as to say that 28 grams of nitrogen gas reacts with 6.01 grams of hydrogen gas to make 34.1 grams of ammonia. It is important to remember, and I will say it over and over again, that we need to know the moles before we can figure out the grams. That the grams is not directly related to the balanced chemical equation the way the moles are. So everything is going to go through moles. Now, a mole ratio is how we describe the relationship in moles between any two substances in a chemical reaction. So we can look at the moles between two reactants, or a reactant and a product, or perhaps two products, all depending upon the particular chemical reaction. When we started balancing chemical reactions, I said always make the reaction in the simplest form. The coefficients needed to be in the smallest number possible, which is what we see in our balanced chemical equation here, where we have 1 nitrogen and 3 hydrogen and giving us 2 ammonia. But the equations are still balanced as long as the proportions remain the same. So if we just double everything and say 2 molecules of nitrogen gas plus 6 molecules of hydrogen gas will give us 4 molecules of ammonia, it is still a balanced equation. We've just increased the proportions. We've doubled it. We could triple it and say that there's 3N2 plus 9H2 giving us 6NH3. So you can see how we've just taken the original coefficients in our original equation up here and just multiplied them all by 3. And you even can go to fractions. You could have 0.05 nitrogen and 2 plus 1.5 H2 giving us 1 NH3. So it's easy to kind of see what happens if we double from the balanced equation or triple from the balanced equation, but sometimes we have to do calculations, and we do ratio calculations when it is not so clear what the relationship is. To do ratio calculations, I recommend you use equivalent fractions because this is a technique you've used in math earlier and it's fairly straightforward, and I think probably you remember what to do. So if we have our balanced chemical equation for ammonia again and have a problem that asks how many moles of ammonia are produced if 4.2 moles of hydrogen are reacted with an excess of nitrogen. That means there's plenty of nitrogen. We're not even thinking about the nitrogen. What we're thinking about in this equation is what's going on with the ammonia and the hydrogen. Those are the two we're going to focus on. And the way that I recommend doing this is over kind of to the side. Make yourself a little fraction that shows the two things you're going to compare. So we have ammonia, NH3, and we have hydrogen, H2. And this is just a reminder of how I'm going to set up my equivalent fractions. Then the next step is you go to your balanced equation and see what is the ratio in the balanced equation. So our ammonia, the original number is 2, and hydrogen, the original number is 3. So that's our first fraction in the mole ratio calculation. We set that equal to an equivalent fraction that is based on the problem. So the problem says we have 4.2 moles of hydrogen, and we want to know how many moles of ammonia are produced. So we don't know about how much ammonia we produce. That's what we're trying to figure out. That's our X. But we know we have 4.20 moles of hydrogen. Notice that the ammonia is going always in the numerator and the hydrogen is always in the denominator, which is another reason I like the equivalent fractions, because you always keep it in the same place. Then you just use the equivalent fractions to solve for X. So with equivalent fractions, you remember you cross multiply. So we're going to cross multiply. We're going to have a new problem that's going to set up saying that 3x is equal to whatever 2 times 4.20 is. So that would be 8.40. And then you would divide both sides by 3. This is just basic algebra. And then we're going to end up with x being equal to 2.8. So what have we solved with our 2.8? Well, that tells us how many moles of ammonia are produced if we're starting off with 4.2 moles of hydrogen. Whenever you're doing a mole ratio calculation, you need to start with a balanced equation. Sometimes a balanced equation will be given to you, and other times you have to go ahead and balance it. So again, we have another reaction with ammonia. This one says that ammonia will react with nitrogen monoxide to produce nitrogen gas and water vapor, and asks us how many moles of nitrogen monoxide, or NO, is needed to react with 2.28 moles of ammonia. But before we can do any kind of mole ratio, we need to make sure that this equation is balanced. And if you look at it right away, you can see we have a problem with the hydrogen because we have 3 hydrogen over here and only 2 hydrogen over there. And so you would go back to your technique for balancing equations. Remember, I suggest that you write out what you have to begin with, which is a nitrogen and 3 hydrogens, another nitrogen and an oxygen, 2 nitrogens, and then 2 hydrogens and an oxygen. And then you would bring down whole molecules. So of course we've got to add another ammonia with NH3. And now we've got 6 hydrogen over here. And so we don't have enough hydrogen, so we're going to have to match up so that we have 6 hydrogen over here. And then we have 3 oxygen, and so we've got to make it so that we have 3 oxygen by bringing down some nitrogen monoxide. And then we count our nitrogen and see we have 5 nitrogen on the left-hand side of the arrow and only 2 nitrogen on the right. So we're obviously not done yet. You would need to continue to bring down molecules to count until you can balance the equation. The first thing I would start by doing is adding more to my nitrogen monoxide. I don't have enough room really on this slide to keep going, so you're going to have to take my word for it that we're going to end up with having 4 moles of ammonia reacting with 6 moles of nitrogen monoxide, producing 5 moles of nitrogen gas and 6 moles of water vapor. So we have to balance our equation first before we can do mole ratios, because we don't know what the original moles are in the balanced equation until we have a balanced equation to begin with. Then after you have that balanced equation, you put your mole ratios in to calculate the exact amounts that you're asked to figure out for the problem. So again, we're looking at how many moles of nitrogen monoxide, so that's going to be our X, and it's going to be reacting with these 2.28 moles of ammonia. So again, as I said, start over here and make a little cheat sheet. So we'll just put nitrogen monoxide and ammonia are the two things that we're comparing for here. So I'm just making myself a little note on the side. Then I go and look at the balanced equation. What are my ratios in that balanced equation? Well, nitrogen monoxide is a 6 and ammonia is a 4. And then I make an equivalent fraction which has the numbers in the problem. We are being asked to calculate nitrogen monoxide, so that's our X, and we're told that there's 2.28 moles of ammonia. So once again, you're going to practice cross multiplication to solve this. You're going to end up with 4x equaling 6 times 2.28. And take my word for it, when you go ahead and do the math, x is going to equal 3.42. So you figured out that it's going to take 3.42 moles of the nitrogen monoxide to react with your 2.28 moles of ammonia. Now, it really doesn't matter whether you're talking about two reactants or two products or a reactant and a product. Any combination of two substances from a balanced chemical equation can be calculated using mole ratios. We can figure out how much we're making. So if we wanted to go on further and say, well, how much nitrogen gas is going to be produced from this 3.42 moles of nitrogen monoxide, you could set up that ratio too. You could look at nitrogen monoxide and nitrogen gas. We know we have 3.42 moles of nitrogen monoxide. We just calculated that out. Oh, I should have put that in the wrong place. Let me quick erase this so as to not confuse you. First, we do the one from the problem. So let's do the one from the problem. So that is 6 moles of nitrogen monoxide and 5 moles of nitrogen gas. So again, we're taking that right from the balanced equation. Then we put in the ones from the numbers from the problem, which was 3.42 moles of nitrogen monoxide, and then X for our nitrogen gas. And again, cross multiply to find the answer here. We're going to end up with 6x equaling 5 times 3.42. And I'm running out of room here, so just trust me that x is going to be equal to 2.85 in this case. So mole ratios are the first step in the process of taking a chemical equation and turning it into an exact recipe with grams of one substance plus grams of another substance to produce whatever substance we're trying to put together. We can't do grams without moles, and we need to know the relationship between the substances that we are considering in order to produce the right amount.